I'm not sure if it helps. You can bring curtains down. Do you see clearly from there? So I want to emphasize that reinforced concrete is a versatile construction material. You can find it in many places in different projects, in buildings, in bridges, in dams, in different sort of projects. You can see a mixture of concrete with other things, mostly reinforced concrete design. And during the past decade, there has been lots of collapses in these kind of structures. For example, the Tahoma Bridge in the States, those are Niigata earthquake in 1964, and another one here, a short column happening in 1986 in another earthquake. So that's why scientists and engineers have tried to figure out what's the problem with the different kind of damages and collapses. And nowadays, we have really a high and good level of information about how to design proper concrete structure. So that's what we want to learn in this module. After this module, it's anticipated that you as a civil engineer is able to design specific building with concrete, should be reinforced concrete design and the foundation. So this is familiar for your eyes. We are working this year only with EC2, Eurocode 2, not any of the others. In structural design, you work with EC3 and EC1 for loading and steel design. This year, for this module, we are only working with EC2. It's already available on the Moodle. I've put it already there. So EC2 in this module is like our Bible. The design code is like Bible. Anything you have doubt, you should go to the Bible to see what it says. So if after graduation, if you see, okay, I don't know which one is correct, this book says this one, that book says that one, you should go to the Bible. Benchmark is Eurocode 2. So whatever it says, you should do that. For a specific design project, there is really a complicated procedure to follow to complete your design process. You really start with client's brief. Client's brief means the client says, okay, what I want. And client is not a civil engineer, and you should have enough communication with them to make it mature that what they want. Then you need to come up with some concepts. Okay, it's better to have a concrete design project here because it's in a humid area and the corrosion is a problem, for example. Then you need to come up with some preliminary design. You had it in structural design. Okay, the columns probably are in this size, the beams are probably on this size. I'm not talking about detailed reinforcement, but it should be like this. This is the preliminary design, and give it to the clients to review if they like it or not, they want to change it or not. And then you need to go to the detailed design and final solution with the drawings that they need to bring to the construction site to erect it. So the whole process sometimes need repetition. That means that you need really computer to be taken into consideration to be able to repeat some parts, and it's really not possible to do it by only hand calculations. And there is also a need for balancing between the different design concepts like this, these and these. For example, this represents the economy, like resources, time, cost, and speed of construction. And these are talking about fitness for purpose, which is about health and safety, maintenance, sustainability, durability, function, and buildability. Each of these, if you increase each of these, you need to pay more cost. Okay, that's why there should be a balance, isn't it? Because we cannot say, okay, I want 99.99% reliability and durability and functionality in my building. Okay, you need to pay 5 times cost as a regular building. Do you pay? No. So there should be a balance between these criteria. And when we come up to the steel and concrete, there are some differences between these two materials. Let's see what they are. For example, for concrete, these are for concrete, these are for steel. For concrete, the concrete has a strength in tension pore. Do you remember structural design? All of the bottom part of the beam is out of calculation. Concrete in tension is awful, isn't it? But steel is good, not bad. Although its buckling is a problem, but if you come up with the buckling, steel is good. A strength in compression. Sorry, buckling is not here, buckling is here. A strength in compression, concrete is good in compression. But steel is good if buckling is not a problem. If you come up with a solution for the buckling, the steel is also good. But buckling still needs some kind of stiffeners or additive members to restrain the system from buckling. From the point of strength and shear, concrete is fair and steel is good. That's why we need to put some surrounded reinforcement in beams, in concrete beams to carry the shears, right? We cannot rely only on concrete to bear the whole shear forces. It's not bad, good, fair, but steel is good. Steel is really good in shear. And for durability, concrete is really good. Steel, not bad, but corrosion is a problem. And for the fire resistance, again, concrete is awesome and steel is poor. This is very important, fire resistance. Sometimes you have a steel design, but you cover the steel elements with some sort of concrete just to have a type of protected type of section for the fire resistance, right? So when we come here, if I had the PowerPoint, this is supposed to come now, but we have everything here together. When we talk about strengths in tension, concrete is poor and steel is good, okay? Every point in your life, when you see something bad and good, you can think of bringing disaster to opportunity. Bad and good, disaster to opportunity, right? You have seen this terminology in social science, etc. It's not an exception here. We can do the same here. Concrete is poor in tension, but if we mix these together to make a reinforced concrete section, it's a kind of disaster to opportunity. We will have a mixed type of section which carries both types of loads very good. So, again, we had too much effects here. We have everything here, but don't worry. This is table section 3.1, page 29 from Eurocode. Eurocode is already on the Moodle. When you go home, just download it and check it if I'm wrong. You should see this table in page 29. This is the same table we worked last year in structural design. So what it is, it gives you the different properties for concrete grades. For example, the concrete grade 3037, we call it like this, C3037. 30 is characteristic cylindrical strength, and 37 is characteristic cubic strength. everything is in terms of megapascal, which means Newton over square millimeter. Okay? So it means that this is a specific type of concrete. This is another type of concrete. From left to right, it's increasing. Okay? This is the most weakest, getting stronger, very strong, the most strongest concrete we can use for our design. Okay? We really, in real ordinary projects, we really don't use these concretes. I cross them out. Why? They are called high strength concrete. They are good, they are very good, but they are high strength concrete and they are expensive to make, to construct. And it doesn't make sense in ordinary projects to use them because it just increases the cost without gaining enough. May I ask everybody, especially you, okay, to put the cell phone down and take part in the lecture, okay? It's better because I'm distracting here, really, to be honest. And you're distracting your friend as well. Let him listen to me, okay? I'm talking to everyone. Please, 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 put the mobile phone down, turn it onto the silent, whatever it is, and let's do something here. I'm here for you. You are here to learn something, okay? This term, we need to learn something. This is the last chance. You're going out of the university. You're going to be graduated. This is the last year. Let's make it useful for everybody, okay? Agree? Let's do it. Where was I? These are expensive. You use it, but in high-rise buildings. For example, if you want to make a 50-story concrete building, you cannot use ordinary concrete. You don't get the correct answers when you want to comply with the codes. The capacity is less than the demand. You have to go for the highest strength concrete. The shear wall for the Khalifa Tower in Dubai is made of concrete. Highest strength concrete. Ordinary concrete doesn't work there. And that's expensive. You don't use these two because they are not a structural concrete, really. You use them for pavement or for some infill walls which are not structurally performance. You know, they're not working for you as a structural element. They are very, very weak here. You probably will look for this green box here. Some of them. This is the very basic concrete, and these are a little bit more advanced. So I just went for 3037 here. And here is where you have received already an email from me that bring a piece of paper and pen with yourself, didn't you? Right? Now we need them. Bring them on. We want to do a practice. We will do this during the semester a couple of times, maybe several times. We want to really do some exercise here. This is the definition of different parameters in that table, and don't be. We only need these 4 parameters. Write them down for yourself. Everybody for himself or herself. Yeah. Get the symbol FCK, epsilon C2, epsilon CU2, and N. These are the parameter. Get the definition, what it is, and we come back to the table to get the values. We only need these 4. First one, FCK, epsilon C2, epsilon CU2, N. Only 4 parameters. We need these 4. Okay. Shall I proceed to the previous paper, the table? Huh? Here? You don't need to write all of the description. Just get the symbols. So how I figure out everybody's happy to proceed. You don't really need, you will have all of them on the Moodle. You don't really need to write all of this description. Just get the 4 parameters and let's get to the table. And we want to take the numbers for those parameters from this table for this type of concrete. Okay? For this type of concrete, 3037. The grade concrete, 3037. What do you want for the first parameter? The first parameter is the characteristic compressive Cyrendical strength at 25 or 8 days, FCK. It is 30 megapascal. It's grade 3037, right? The first number is FCK. So the second number is epsilon C2 and epsilon CU2. These are provided here. This is epsilon C2 and this is epsilon CU2. Epsilon C2 is 2. Epsilon CU2 is 3.5. In terms of percent, yes. It means that it's 0.002. And the next one is 0.0035. You need to divide these numbers. When it says percent, you need to divide each number by 100. Okay? When it says epsilon is 2, it means it's 2 divided by 100 because it's in terms of percent. Okay? Does it make sense? Epsilon 2u, epsilon C2, here it's 2. Epsilon CU2, it's 3.5.
0.035.
Yeah, divided by 100. What is the fourth parameter you want? N. N is here. It's 2, right? Take a note. So you already have those 4 parameters, right? You already, anybody doesn't have these parameters. Okay, is it clear? If you change your concrete grade, they will be changed. Okay, if you want to use something else, okay, they will be changed. Just go to this table. You can repeat it for another grade of concrete. So we have these 4. We are here. First of all, pardon me?
I have one doubt with the table.
Louder, please.
I have one doubt with the table.
Okay.
Why is there no other value given for other concretes, just 30 and 37?
The same as this one.
Yeah.
These are the same. All of when they are empty. This 3.5 is in the middle of this cell. This red one, I have added this third one. All of these cells are merged together. 30. This is for all of these. Okay. Anything else?
No.
So, do you remember in some point you have gone through the lab and you probably have done some experiment like this? In a cylindrical type of sample of concrete, you crashed it and you read the force and you had the area of the section, you divide it, you came up with some numbers. That number is this one, this 30. FCK. FCK is this one. You have done this in the lab already. No? Okay, cube is the second number. 30, 37, there is a relationship between them. The first one is less than, almost 10 to 20% less than the second number. If you do the cubic one in the lab, you will get something like, for this type of concrete, something like 37. But the FCK is less than that. There is a relationship to transfer them together. And it's around 30, right? So
wait, 30 is FCK.
What is FCK?
30.
Yes. 30 is FCK. Huh?
What's 37?
The strength cube strength.
FCK cube.
I don't know, the symbol should be, no, this is cylindrical. No, it's not here. No. It's not here.
What's the symbol?
This is FCK cube. FCK cube. Okay? This is the second one,
What's
right?
the difference between, 30 is a cylinder, 37 is a cube.
When you go to the lab for a particular type of concrete, if you make one sample cylinder, one sample cubic,
They're different, yeah.
if you crush them, always the number you get for the cylinder is less than the cubic. And there is a reason for that because of the shape. And what we use for the design is the lower number, is the cylinder one. We don't use 37. This 37 is here just to respect the old people that were used to use this number a couple of decades ago. We just respect them.
So does this even impact the building? If you're making round pillars, it will be less than the square ones.
Yeah.
Square is better.
What?
If you're making the columns of a building which are round, so that would also be impacted by the same thing?
No, not really. It's for only the material. That concrete is a hybrid thing. It's a mix of concrete and reinforcement. The behavior is different. This is the pure concrete. Okay? Now, this is just the pure concrete, and we don't really use 37 in any sense. That's there really to respect a couple of old codes. I don't know, 50 years ago they used to use that, but in some point they changed to cylinder type of strengths, which is 30. Okay, we only use with the first number. So are you happy? Everybody happy with the table and these 4 parameters? We are here. Again, when you're at home, check if I'm wrong. Again, we go to the Bible, EC2, section 317. Okay? You should go to the Bible, make your eyes comfortable, familiar with those kind of writing. This is very important. I just cut some pieces, bring it here. Just go there and read the other parts. Just get yourself familiar with the type of code writers, authors. So this is coming from Eurocode, and there is a formula here. These 4 green parameters are the things you have already, aren't they? Right? Don't worry about FCD. FCD is a fraction of FCK when we decrease it for the uncertainty stuff divided by 1.5. Don't worry about it. You can put FCK, forget about FCD. You can put the 30 here. Don't worry about the safety factors. But we have these 4 parameters. We want to make a graph representing this one against this one. Everything else is clear, isn't it? Everything is number, 1 minus 1. We have these 4. We want to represent sigma C versus epsilon C. Sigma is stress, epsilon is strain. Do you remember strengths of material? Sigma is stress, epsilon is strain. Sigma is a kind of force, epsilon is a kind of deformation, but normalized deformation, right? Because you divide force, for example, if it's compressive, you divide force to the section area, you come up with the stress, and the strain is the deformation divided by the lengths of elements, right? It's a kind of normalized representation of the force and deformation. Sigma, epsilon. We want to the Eurocode gives you the relationship between these two parameters, okay, as a formula. We want to draw this in a graph to see if it's what we want to expect to. So again, we have every solution on the screen. This part is coming from Eurocode. The shape should be this, okay? The shape should be this. This part is from Eurocode. This part from me, okay? Wait before you calculate anything. There is on the Moodle, there is a supplementary material for lecture 1 beneath the lecture 1 slides, which is, you can expect what it is. It's an Excel sheet. Doesn't have Microsoft Excel here. Wow. What computer is this? What does it mean? Oh, it has. Okay. I already have put all the calculation in the Excel, and this one is this one is exactly this one I'm talking about. The practice we are doing is, you on your papers should try to capture one of the points to see if this is correct or not. Okay, you can see, for example, if you get, for example, here, it should be -10, something like that. I want you to show me you prove one of the points for this graph. But before that, why this graph is at the bottom and this graph is at the top? The reason is, I'm talking now about the compression. That cylindrical sample, okay? Under the pressure, under the compression, I want to crash it, okay? The force is compression. Because after this, I'm going to talk about tension. As a convention, most commonly convention, I'm saying tension forces are positive, compression forces and stresses are negative, okay? So because I'm talking about negative forces, about the compression forces and stresses, that's why I'm doing everything in the minus part of the graph. Epsilon is minus, negative, and sigma, this is epsilon, and this is sigma. All of them are negative because I just mirrored it down. I'm using this, but in the negative part, just to emphasize that this is compression, this is not tension, okay? I want you to prove me with those 4 parameters, put those 4 parameters in this formula and select one epsilon c arbitrarily, up to you. Prove it, this sigma c is correct on these graphs. Let's do it. This is the activity we want to do. Louder, please. For the formulation? Okay, good, because nobody sees the, yeah, that's better even. You don't see the solution. Let's do it.
Are we supposed to select our epsilon c?
Arbitrary, I said, but from
As in, yeah, like
from
the
0
range.
to something like,
2, I think.
you only have, you should go not more than 3.5%. Okay, something between 0 and 3.5%. You've got 2 epsilons from that table, right?
Yeah.
Let's do it. The first person provides me with the first point will be received a round of applause. Except Yashir.
From 0 to 2%. You can take any of the number.
Yes, I thought we needed these.
Yeah. More than C2. Is the EC a percentage?
Which EC epsilon C? Yes. Yeah.
0.597.
For what point?
Well, 0.02.
No, okay. What?
Because you said 0 to 0.05.
Yeah. So what you get from that point?
Because 0.5.
Right out of 0.959 almost 0.6.
I use 0.02 for my EC.
Let's see if it's
You should
correct.
get this one.
You know the N?
Yeah.
Do that.
Yeah.
No, it's not correct. You are here. You should get minus 20 or minus 30.
Where am I?
So I got something like minus.
Okay.
How do I get that?
So I got that.
Did you multiply it by 30?
Did you get this?
Yeah. Use this.
Did you multiply it by
Use
30?
the top. It's meant to be from 0.0, from 0 to 0.035. But yeah, EC. I use 0.025.
Oh, I'm taking high numbers.
That's the most common.
0.025. Where do you get that number from?
But he said you can select from a range from 0 to 0.035. That's just what I get.
Why is my answer different?
I know that's 1.875 for 0.025.
It's got 30 now.
Yeah. I think you like.
It's wrong.
Okay.
Why? Because you forgot one minus in the formula.
Ah, I
There is
see.
a minus
Yeah,
here.
yeah, yeah.
These are the most common mistakes you. Yeah. Louder, please.
Is it like 24.489?
I got 2 years.
Were you painting?
No, my youngest sister.
Yeah, this is good. Good, Jesse. Yeah,
Very nicely decorated.
Yeah, this is good.
Go on, send it.
That's good. Good. I just wanted to show you that as far as this is not really complicated, this is a formula, but we do some human mistakes. You just forget to add one minus, you just forget to transfer one of the numbers into the percent, but obviously some people do correctly. The aim, I just did it because I want to show you what I'm going to do this year. I wanted you to practice, to minimize these kind of errors. This happens when we do it manually. This happens when we work with ETABS. This happens when we do drawings. If we practice, we will get more skills to avoid these kind of issues, okay? But it's okay. Doing mistake is totally fine. It should bring you some skills when you try to find where was the problem and correct that. How does it make sense? So, the solution is here, and there are two graphs, just because if you use 30 here, you will come up with this graph. But if you divide your 30 by 1.5, which was safety factor, if you remember, FCD is always FCK divided by 1.5 for safety. If you use 30 divided by 1.5, you will come up with this one. So these two graphs are almost same, but with a difference of 1.5 division. All right? So the epsilon varies between 0 to 3.5 in terms of percent. Everything should be divided by 100. And this is megapascal in terms of stress. The maximum is 30. Let's talk about this. The maximum is 30, okay? When you, in the lab, when you press your sample, it means that you're increasing the tension by the machine. You're increasing the tension here. The machine presses your sample. You're going here, okay? You're going here. When you go to the 30 here, it is pressing your sample, and your sample is get pressed, okay? Gets smaller. Still, I'm having a strain. I'm the sample, okay? It's pressing me. When we reach to the 30, still I'm shrinking. It means that the epsilon is increasing, okay? The smallest length of the element, okay? In some point, it will crash, which is epsilon Cu2. The parameter you got, epsilon Cu2, right? In that point here, somewhere here, you will see this will crash. That's the behavior of concrete. That's the behavior of concrete without reinforcement, just pure concrete. We want to do the same for steel. Eurocode has provided this formula, some other formula for steel. We want to do it for steel. But if you need, we can have 10 minutes break, just to stretch your leg, get a water, and come back. It's 8 minutes past 12. Let's come back here at 17 minutes after 12. Please don't be late. Does anybody mind if I open a
Give me a second. 5 minutes. Give me a paper. You're done. Have you done the calculation, please? Well, they just assume it. You have to assume all of the numbers. Wait, where is the EC in this graph? I have a doubt. Which one is the EC in this graph, like EC2? And which one is the stress? Like,
which graph? This one or this one?
one. This is the component.
This is stress. This is strain. This is
The stress.
this one.
So this is the
Yeah,
this one.
sigma C. Yeah, this is sigma C.
So when
This is epsilon C.
epsilon is multiplied by
Yeah.
Can I ask that my
without any number.
Wait.
Yeah. This is this point.
Wait. They depend 0.2,
We
right?
got one
So
for epsilon.
0.2 is like the
This
minus
is
2 there. So the
so
answer
it
should
should
be
be around
20.
between 20 and 25, which is 22 points.
That's why it's minor.
So you should put 30, you should put minus 30. You should put minus 30, right?
Yeah, but it's easy.
Pardon me?
It does not say EC2, so that's not.
Yeah, that's what I was saying.
For which point? You should assume epsilon and calculate sigma, not vice versa. You should assume this one, but calculate this one. Any number from this. Okay, you said, okay, I will get 2.2 here. You should get this number. But it's better to get something here, like get between 0 and minus 1 half, 0.5 divided by 100.
So we need to choose from here to here.
Yeah. This is x-axis, this is y-axis.
How did we verify that?
It's just a question about the
Where can you see
classification.
Yeah.
At work, we changed from Gen 3 to Gen C25 to 30, and I'm just reading their specifications, and it's just minor adjustments. So
From, you mean,
Gen
from,
3 to
So it's 2.
what do you mean Gen 3?
Gen 3 concrete.
Can you open the graph?
Is it not there?
No.
So we use C25 30, so
So this is a
Yeah.
level lower.
yeah.
So it's not, the difference is not too much.
No,
No.
it's just the aggregate.
Okay.
Yeah,
It
yeah.
should be here.
And the ratio of cement to water, and water to
Okay.
cement, yeah.
I don't know how
But
to verify.
if you want to produce any sort of better concrete, you need to have a plan to
Yeah.
select the right aggregate, right amount of cement and water. So this is the work the company is doing. So you buy, okay, you order concrete, I want this type, so you should prepare it like this.
Yeah, yeah, because that's
And you do a sample in the construction and test if they are correct or not.
Yeah,
Yeah, it's enforcement, so we should test if they are.
because it's for underpins, so
Yeah.
it's really important.
Yeah, that's very important, because you cannot use the concrete and say, okay, I assume that's.
Yeah, no, you have to test it because
Yeah, you should.
it's a historic building and
Yeah.
it'll just collapse if you
Yeah.
don't do it properly.
Yeah.
Yeah.
Okay.
But you can start from here, not this one, these two, not
They're too big, aren't
Yeah, they're too, this one upward.
they? Typically, this is what they
Typically,
use.
one of these three I use, maybe this one or this one. It's okay, you can use this one. But this is the most basic one, right?
Yeah.
Yeah.
Okay.
Thank you.
Sometimes I need help. I don't understand this.
We still didn't get the number.
No, we get the number, but I don't get, how do I verify the number on the graph?
What epsilon did you go for?
0.0.
0.0.
Sorry, 0.0.
Okay, what you get as the sigma.
2.22.
What?
This one.
24.50.
That's correct.
How do I verify it? Like, I don't.
First of all, it's minus 30, not positive 30, and this is minus 34. It's, the epsilon is, let's
It's
say, 0.02, it's here.
So,
Something like 30, yeah, you're seeing.
so is FC.
Which one is this? Isn't this the line? Or is it?
No, this one is for your case, because it's then divided by 1.5.
Okay, but it's 2, right? So it should be somewhere around 30.
Can I ask, if the FCK is 30, so FCD is given by 1.5, right?
Again?
FCD should be divided by 1.5.
Yeah.
So if you divide by.
1.5.
This is for FCK, this is for FCD.
Oh.
If
Okay.
you're working with FCD, compare it with this.
Okay, what did you get?
Which one is FCK?
The last one.
This.
The last
FCK
one.
is this one.
Oh, okay.
FCD is this.
All right.
Wait, but I see
So roughly-
24 here and it's like 25 almost, and this is 30. So it's a
Again?
It's 24.50 here, and it's
You don't have a
30.
challenge.
Yeah.
That should be fine, isn't it?
There's some special calculations.
What is this?
Yeah.
Yeah, what's this?
And that is not as well, so I have to do a lot of air drying. might be a table.
Yeah, it's 0.02. But that means 1. And then
Okay, this is wrong. Okay, so this doesn't make sense.
Why?
The answer is, this is wrong. This calculation doesn't make sense. Because the epsilon C.
No, just change this number.
Okay, I know.
0.02. Yeah. Pack your card there. Right word. Tap your card here. Wait.
Okay, then it's 30. Now it makes sense.
Okay.
Yeah, now it matches.
Okay, good.
Should be 0.02. It's fine. This gets cancelled out. This becomes 1.
Can you find yourself? Spell your name. Just can you type it here?
And then this is 40.
That one.
A lot of people haven't come in.
And 2 is 30.
Oh, yeah.
So it was correct all the time. Like, what if I was just correct? But just because the
It doesn't work. This one? Yes, please.
FCD is 1 divided by 5, but if you don't divide it by 30, then this is the line.
Just check the other one.
And this is
By module.
just use this is not
Zero.
FCU2, it's FC2.
Record
Take a formula here.
PA. Create non-type register.
It's 30, isn't it?
View existence. Record existence.
This is 0.02.
This one?
Yes, please. So could you put me as well? It didn't work on the above. Just above.
Which one? This one?
Yes, please.
Okay.
Thank you.
You're welcome.
Sorry, I'm the last 5 minutes.
Yeah, actually,
Okay, let's continue. Eurocode has the same things for reinforcement. Have you seen something like this in lab, or have you done something like this in lab? Tension, yes. You bring concrete to crash it, you bring reinforcement to the lab to see how much is the strength in tension. So it's just forcing the tension for this reinforcement. This is coming from Eurocode 2, from section 3.2. First of all, you need to go to Euro 2 to see if I'm right or not. If you see this there, you should find this in this section in Eurocode 2. That's the Bible, and you need to go there to get yourself more familiarized with the Eurocode. And again, if you use the conventional steel, you don't need 5 parameters for the steel. The steel is very more sort of predictable behavior rather than the concrete. So you really need just this point, just to connect 0, 0 to this point, right? And it goes on. So I really did the most common type of steel, which has 500 megapascal strengths in tension, and this is for the normal 500, and the second one is when you divide it by 1.15, if you remember, as a safety factor. For the steel, we used to divide everything by 115. For the concrete, it was 1.15. For the concrete, it was 1.5, wasn't it? So, this is for characteristic, this is for design. I put everything in the positive range of X and Y because it's tension, just to be comparable with the previous one. Again, I review, this is the strain, this is the stress, but these are in tension, the previous one was in compression. We are doing the same thing for steel, okay? We are doing the same thing for steel. This is the reinforcement. In the lab, we are just applying tension to make it crash. And the behavior of steel is like this. It's quite more predictable than concrete. This is epsilon, and this is sigma. This is strain. This is stress. This is, again, steel in terms of percent. You remember we were working about 3.5 here for concrete, but the steel goes to 7 something. It goes farther than concrete. And here we were working about 30 megapascal, right? Divided by 1.5 to get 20, right? We were working here, right, for the concrete. Now we're working for 500. It's way far away from that one. That's the difference of concrete and steel. That's the main difference. To better understand this difference, I want to put this graph and the previous graph, this graph for steel, and the previous graph for concrete, all together in one place and take a look at it. This is a good idea. Just to see how they look like when they are beside each other. Okay? That's what we are going to do in the next slide. I didn't do anything special, rather than this part is coming from steel and this part is coming from concrete. I intentionally put this part in the negative part because it's compression and this part is tension. You can see the steel behavior is gigantic rather than concrete behavior, right? That's the difference. The steel works awesome in the tension part, but not good in the compression part because of the buckling. Do you remember? When we want to compress some sort of steel sections, we have lots of problem with buckling. On the other hand, vice versa. For the concrete, it works good in compression, although it's 30 megapascal, for example, but it's something good, not bad. But it's not good in tension. In tension, concrete spoils. We don't have anything from concrete in tension. Concrete doesn't work here, it works here. That's why I didn't continue this here, because if I wanted to continue this behavior in the tension part, I just needed to do some point here, like this. Nothing. When you enter, you spoil. If I didn't continue this one, the steel one in this part, because I really, if I want to do that, it's a small piece here. Forget about it. Let's do a mixture of these two. One is good in this one is good in that one, but they both are not good in the other's skill. That's why we go for a sort of composite action, a mixture of concrete and steel. If you remember from structural design, it was the common practice. We had a simple beam. When the load is like this, it's a simple bridge on a river, for example. I'm standing on the bridge at the middle. my load is in the middle, the deformation is like this. Obviously, the top part of the section is in compression, the lower part is in tension, and concrete is not good in tension. That's why we put the reinforcements at the bottom of the section to design it, not at the top of it. There is some cases we put both at the bottom and the top, but for these kind of loading, we put here the reinforcement because we anticipate the reinforcement should work in tension, not compression. If you put this reinforcement at the top, it doesn't do anything because the compression is already tolerated by the concrete. So the concrete bears the load here by compression action, and the reinforcement bears load here by tension action. And the mixture of these two is called reinforced concrete. That's why we don't use concrete alone or reinforced alone. We use reinforced concrete. We call it RC sections, reinforced concrete. Wherever you see RC in this module, it's reinforced concrete. Okay? There are two books. Which are very useful. For example, this is coming from one of them, Mosley. Some of them are coming from the others. They are both available. See the Moodle resources and materials. I provided both of them in full PDF for you. Design of steel elements for Eurocode. This is Mackenzie, and you really only need one of the chapters. We will go from this chapter really. Chapter concrete, chapter timber, which one? Structural steelwork. Where are you? This one, chapter 6. We'll go through this chapter 6, but with a combination, we will go through this, but with a combination with some, this is the main reference, but with a combination of something additive from the second reference, which is Mosley. Mosley is the whole book. The previous book was about everything about Eurocode. Concrete was one chapter, but this book is particularly for concrete, nothing about steel. So this book is some sort of, we will grab some piece from this book from any chapter. Not all of them, but from any chapter. For example, when we want to design beams, we will get something from this chapter, for the slabs from this chapter, from column and foundation. But nothing from pre-stressed concrete, water retaining concrete, no, nothing from them. As I said, it's very simple. We will focus on 4 things for the whole year: beam, column, slab, foundation. So if any chapter is about something else, we are not going for that. Okay, is it clear? So the first is the focus, the second one will complement what we go through.
Was that beam, column, slab, foundation?
Yeah, beam, column, slab, foundation. These are the 4 necessary parts that you have to learn. They are mandatory for a civil engineer to know what to do when you're faced with these. Any other stuff can be done when you face them in a specific project. You will be able to cover that. This is the main thing we need to learn in this module. So there are a couple of other things I just go through. I just said my main word for today, but I just want to mention a couple of more points. There is still a sort of uncertainty in the problem. For example, if you really make some concrete and do some samples, all of those samples are not 30 megapascal because it's real life. You're working with the real life. There are some uncertainties. So there are always a distribution for the samples. I mean, if I really make a bunch of concrete for this grade and we do 50 samples and bring them to the lab and crash all of them, you will get some numbers that you can fit a histogram on it. But the middle what part we do use really? We do use really this number because we want to be in the safe side. That 30 is here. So it means that when we tell you use that 30 megapascal, if you really go to the lab, you might get something more than that 30. And don't be surprised because we use that 30 for the design purposes and we want to be in the safe side. So if you go to the lab, you might get 35, 38 megapascal for regular concrete that you order for that. So good for us. And also there is a relationship when you make a concrete, when you mix the concrete, it's some sort of liquid, you know. You pour it, but after you pour it, you need to cure it. It's like a baby. At least for 28 days, at least. Okay? These numbers, 30 megapascal and etc., they are called the strengths of the concrete at 28 days. At the 28 days lifetime of the concrete, it reaches to the most meaningful number for the strengths. After that, it will be increased a little bit more, but we deny this part again for the safety. It means that when we design for the 30, it's a little bit more, and when it passes 28 days life, it will get a little bit more strength, but we do not count on this part of strength because we want to still have more safety factors. But do not rely on any sort of concrete before 20 days. This is the day life of the concrete. Here you have made the concrete, just poured it. It's not starting from zero because 1 hour after pouring, it has some strengths. So you don't need to wait for a full day. So after 1 hour or 2 hours, you have a minimum sort of strengths.
If you pour retarder on it, would that be significantly different?
It depends. You should consult with the company that is providing for you, because sometimes there are some specifications that prohibits you to add any extra things on it. So it might result in grabbing water from it sooner than it should be, and it makes concrete worse. So the idea is the concrete should rest in a sort of humid area, a humid environment for at least 28 days to be cured. It's like a baby. But the most important thing is that the environment should be humid. From the day you pour the concrete, after that, not when it's wet, when it's a little bit dry, not wet, you should pour a little bit water surrounded on top of it just to make it wet, humid. Otherwise, it will get dry soon. It needs water to be mature. So that's why don't add anything extra rather than it is advised. You know, it can make the process worse than you think. But don't load your structure before 28 days. Okay?
Let them make like a shell and core, like high rise.
Uh-huh.
How long do they have to wait until going to the next level? 28 days.
Awesome question. That's a very awesome question. Yeah. If you go with traditional methods, yeah, you should make one story and wait for them, open your instruments, go to the next one.
Yeah.
Okay. But now there are some new technologies that it's like this. They are working like a hydraulic process. They are here. You pour concrete. They are moving up tomorrow. Pour another one, moving up. The bottom is getting dry. You're pouring new one. It's like going up with hydraulic system. You don't open them and close them. Yeah, it's moving up, and some of them are like, do this story tomorrow, the next story. Some of them are continuously working, like this, 1 centimeter per hour. It's moving 1 centimeter or 5 centimeter per hour, and they calculate that. And they pour concrete from the top continuously, 24 hours, 7 days. And they calculated that the bottom part is getting dry, the top part is getting poured. So it goes to the top. That's it. So when you go to the constructionarium, you built your last year they built a bridge, and for the last photograph, all of the 30 students went there and took a memory photo. Don't do that if you ask me. Not because I know it doesn't collapse, it's concrete, we have too many safety factors, but we have civil engineers. We do not load a concrete structure before 28 days of stand beside your creature and take your photos. You're a civil engineer. Do the right thing. Before 20 days, 1% is okay, but not 30% on a small kind of bridge, and it's a significant load on it. And if you want to go alone, 1 or 2 people, that's fine, because that's a very small amount of load. But significantly loading a concrete structure before 20 days is not good. So, when we work with normal concretes, like I was here, 3037, or the first one was 2025, you remember in structural design, we had module of elasticity for the concrete 30. If you use high strength concrete, the module of elasticity will be increased as well. This is because it's high strength concrete. This table only indicates that if you go for upper grades of concrete grade, that the module of elasticity will be more. It means that it's tougher. For just to indicate that the module of elasticity is not constant for all of the concrete grades. And for this is for a steel. This one is for a steel. For a steel, it's always the strength is for normal steel. It's 500. We just had it in a few slides. 500 megapascal for the tension. It's mostly 500 based on BS. So this slide aims to say that all of these calculations, this is the Excel file, it's already on the Moodle. Please go, when you go home, download it, open it. You did one of the calculations here. For example, Yashir, you did this one. Which one is concrete? Well, no, sorry, you did this one, for example. You did, I don't know which one was that. One of these, whatever you have done today is one of these calculations. Okay, for this epsilon, you got the signal. Okay, but the awesomeness of Excel is when you do one calculation, you can repeat it for a long line of other values, as we have used it for structural design last year, didn't we? So just go and check. I put these Excels, and I will reward any students that find any flaw. I like that's just to promote, just to a kind of advertisement to engagement, increase engagement. Any student find any flaw in calculation, like I found today for a couple of you, will be rewarded. Just go and try to find.
Is there flaws? Have you intentionally?
No.
Ah, okay.
That's a good idea. I can do that. Yeah, why not? Next Excel. Let's do next Excel.
Okay.
Why not? Yeah, why not? That's a very brilliant idea. Because it's already on the Moodle. Next one, I will put intentionally a flaw, and the first one who finds the flaw and email me will get the reward.
That's the round of applause.
No, it's something better.
What's the reward?
Something adding to your coursework. I mean, Mark.
We're going to use this.
5 mark for extra for the course. Good?
Okay.
Not bad. No, it's not hard. How can you hide it?
I don't know.
No, it's not possible. I should put it somewhere in those formulas. It's not. There is no other way to put it. And it's not infinity. It's just some cells. You should, in the worst case, you should check all of the cells. Right? Why not? Let's play with the marks, and that's the best way to engage students into the process. Why not? Yeah. Next Excel. Your idea. I like your idea. So whatever I talked about today, they are in this Excel. Just go there and get yourself familiar with Excel and do a couple of more calculations for some other numbers just to see what I've done there. And let's see what happens.
Formulas will be on the cells, won't they? How you did it, sorry.
I don't hear you.
The formulas for each of those calculations, they're on the cells, right?
Yeah. See, for example, for the concrete, this is the formula you were using, right? If you click here, you will see the formula.
Yeah, thank you.
You're welcome. So this is the Excel. From this slide, I want to emphasize that probably will depends, but we will go through different topics in designing. Don't worry about them. But for every topic we're doing, there will be one or more than one piece of Excel to facilitate the process of design. This is the only way professional designers do. You need to have some pieces of Excel or other softwares. There is a software named MATCAD, not MATLAB, MATCAD. That's brilliant for these kind of stuff. If anybody is familiar with MATCAD, you can use that one as well. The difference between that and this one is when you use that one, it's like a reporting. You're already writing your report. It's like a free space of sheet. When you write sigma is equal to something, it is formula there, but it's your report. It's like, let's say this way, it's like you're writing in Microsoft Word, but the software understands this is a formula, it should be calculated from this range to that range. And at the end, you can print it as your engineering report. That's something awesome as well. MATCAD. It is a family of that company, MathWorks, which provides MATLAB. This is another software, MATCAD. That's something awesome as well. So in this here, we will have 3 main references, nothing more really. There are 2 books, I already told you. Sorry, these are 2 books. One of them is, this is the main book, this is the complementary book, and this is the Bible. This is the Eurocode. They are all on the Moodle now. We have only these 3. I'm not like providing you with 20 references, go and read, and I know nobody's gonna read them. We only have 3 books. If you don't want to read this one, just read this one. 1 book, 1 Bible. That's it. We are gonna be engineered this year. Okay? Engineer means a lot. Engineer means you should look at that building and figure out if it's that okay or not, if this structure stands still there, if it's good or not, if this beam is too much for this building or not. After a few years, you will get this. But here it is the beginning of learning those kind of skills. So I also put some useful YouTube short videos. You don't have to do anything rather than watching them. They are brilliant, available videos on YouTube to better understand the behavior of concrete from experts around the world, other experts around the world. I don't know how many they are, but there are 12. There are 12 clips, videos, short videos, some of them might be a little bit longer, but just go and watch, if you can, all of them, if not, whatever you like. They really help you to better understand the concrete behavior. They are useful. And the last but not least, if anybody is interested in linking these things to the research You can do research on concrete design as well. This is not part of the course, but if you go as far as you have Google, type Google Scholar in the Google, and you will be directed to another Google, which is called Google Scholar. This is Google Scholar, okay? No, sorry, this is not Google Scholar, but it's coming from there. In Google Scholar, Google is for searching for anything, okay? But Google Scholar is specifically for searching for academic papers, books, references, stuff like that. If you're interested to do research for your final project, for your master degree maybe after this, for your PhD dissertation, for any sort of other research, you want a reward somewhere, you need to go to the Google Scholar and do some search to find relevant papers related to concrete design, and there are lots of these things there if you're interested to do so. It's good, always it's good to connect teaching to the research and benefit from the last findings from the research into the teaching process, and this is what we will do in some points during the whole academic year. That's from me today. Is there any question from you? How did it work today? Good. We will do it more, and I got a new idea from my friend. I will employ that as well, and we will have, I promise you, we will have quite interactive during the year to learn this module in practice, not something that we will forget after 1 month you leave here.
Yeah.
Something really useful if you go either in the consultancy or in the construction side. Good luck.
When is the first course